The next theorem to be introduced is known as Thevenin's theorem. This theorem permits the reduction of a complex network to a simpler form, and the simpler form can be used for design and analysis purpose. By applying this theorem, any two-terminal DC network can be replaced by an equivalent circuit consisting solely of a voltage source and a series resistor as shown in the figure. In other words, using this theorem or by applying this theorem, we can reduce any complex network into an equivalent simpler form, which will be represented by a voltage source represented by E Thevenin and a series resistance associated with it represented by R Thevenin. The steps which needs to be followed in order to apply Thevenin's theorem are as follows. Consider this network to be the complex structure, and our aim is to reduce this complex network into its simpler form. The first step is to identify the load resistance and remove the load resistance from this complex structure. The next step is to mark the terminals where we will be applying Thevenin's theorem. The third step is to determine R Thevenin. In order to determine R Thevenin using this complex structure, we need to deactivate all the sources. The voltage source must be replaced with its short circuit equivalent, and the current source must be replaced with this open circuit equivalent. And after that, we need to determine R Thevenin. After determining R Thevenin, the next step is to determine the Thevenin voltage, which is E Thevenin. The next step is to determine E Thevenin. E Thevenin is basically the open circuit voltage between the marked terminals. In order to determine E Thevenin, we need to replace all the sources as it were connected in the original network. For example, for this particular network, E Thevenin is equal to the open circuit voltage between the marked terminals A and B. So, in order to determine VOC, we need to reconnect the voltage source E and the current source I as it was in the original network. Then we have to determine VOC. The final step is to draw the Thevenin equivalent circuit with the load resistance which was removed in the very first stage. Let us go through some examples to have a better understanding of the theorem. Problem 4. Find the Thevenin equivalent circuit for the network in the shaded area. That is, for this particular network, we need to determine the Thevenin equivalent circuit. The load resistance RL has already been marked in this case. Now, in order to determine the Thevenin equivalent network, we need to determine R Thevenin and E Thevenin. To determine R Thevenin, the first step would be to remove RL from the original network. The modified network will look like this. The next step is to deactivate the sources. In this case, we have only one source, that is an independent voltage source. So, to deactivate the voltage source, it will be replaced by the short circuit equivalent. Then, if we determine R Thevenin is basically equal to the parallel combination of R1 and R2. So, R Thevenin is equal to 2 ohm. The next step is to determine E Thevenin. E Thevenin is basically the open circuit voltage between the marked terminals A and B. Now, if you observe carefully, the voltage at this node and the voltage at this point is same. Similarly, the voltage at this node and the voltage at this point would also be the same. Why? Because there is no connection between point A and B. These 2 points are basically floating. Hence, E Thevenin, which is the open circuit voltage, is basically equal to the voltage drop across resistor R2. Using the voltage divider rule, we can easily determine the voltage drop across R2, which is equal to 6 volt. So, R Thevenin is equal to 2 ohm and E Thevenin will be equal to 6 volt. The last step is to draw the Thevenin equivalent network along with the load resistor which was removed from the original network in the first step. Now, if you observe carefully, the load resistance RL has the symbol of a variable resistor over here. One advantage of Thevenin equivalent network is that on changing the load RL, we can easily determine the current IL flowing through this branch. Problem 5. Find the Thevenin equivalent circuit for the network in the shaded area of the network. So, we have to determine the Thevenin equivalent for this part of the circuit. As mentioned earlier, in order to determine R Thevenin, we have to deactivate the sources and also remove the resistance R3. So, deactivating a current source is basically replacing it with an open circuit equivalent. If we do that, then R Thevenin will be equal to the summation of R1 and R2, since R1 and R2 are connected in series in the modified network. Hence, R Thevenin will be equal to 6 ohm. The next step is to determine the open circuit voltage over here, this terminal A and B. Now, as I have mentioned earlier, that A and B are basically floating points. That means there is no connection between point A and point B. Hence, there will be no current flowing through these two wires. That is, the current flowing through the resistor R2 will be equal to 0. Now, if current flowing through R2 is equals to 0, then the potential drop across R2 will also be 0 volt. Hence, E Thevenin, which is the open circuit voltage, is basically equal to the potential drop across resistor R1. So, using Ohm's law, we can easily determine the potential drop or the voltage drop across R1, which will be equal to V1 equals I1 R1, which is equal to 12 times 4, 48 volts. Hence, the final step will be to redraw the Thevenin network with the resistor R3, which was removed at the first stage. Hence, E Thevenin equals 48 volts, R Thevenin equals 6 ohm, and R3 will be equal to 7 ohm. Problem 6. For this particular network, we have to determine the Thevenin equivalent circuit. Well, the first step would be to determine R Thevenin. In order to do that, we have to remove the load resistance RL and deactivate all these sources. So, this is how the network will look. 4 ohm and 12 ohm are connected in parallel, and this combination is connected in series with 1 ohm. Hence, R Thevenin will be equal to 4 ohm. The next step is to determine the open circuit voltage, which will be equal to E Thevenin. In order to do that, we must reconnect all the sources which were previously removed. As I have mentioned earlier, that point A and point B are basically floating points. Hence, no current will flow through these two branches. Thus, the potential drop across the 1 ohm resistor will be equal to 0 volt. So, V Thevenin becomes equal to the voltage drop or potential drop across the current source. We can determine the potential drop across the current source by applying mesh analysis in these two complete loops. There are two unknown currents, hence there will be two linear equations from these two meshes. On solving these linear equations, we will be able to determine the voltage drop across the current source, which will be equal to the voltage drop V Thevenin. The solution for this problem is given over here. Please go through the solution very carefully in order to determine V Thevenin. The final step is to draw the Thevenin equivalent network along with the load resistance which was removed in the early stage. According to the second portion of the question, the variable load resistance RL is now being varied, and for each value of RL, the current IL is being determined using Ohm's law. When RL is equals to 6 ohm, IL equals 3 ampere. When RL equals 16 ohm, IL equals 1.5 ampere. When RL equals 36 ohm, IL will be equal to 0.75 ampere. Problem 7. This circuit contains a dependent source, unlike the circuit in the previous examples. To find R Thevenin, we usually set the independent sources equal to 0. That is, we deactivate them. But this cannot be done in case of the dependent source. Because of this, we excite the network by connecting a voltage source V0 across the terminals, as shown over here. We assume the voltage of V0 to be equal to 1 volt. Now, if we can determine the current through this branch, which is I0, then we can easily determine R Thevenin, which will be equal to V0 by I0 according to Ohm's law. I0 is basically equal to minus I3. We can determine the current I3 using mesh analysis. So, this is the method which will be followed to determine R Thevenin whenever there is a dependent source present. While determining open circuit voltage VOC, the procedure is the same as we have used in the previous examples. So, applying mesh analysis, we determine the value of I3, which is equals to minus 1 by 6 ampere. As mentioned earlier, I0 is flowing in the opposite direction to I3. Hence, I0 will be equal to minus I3, which is equal to 1 by 6 ampere. We have already assumed that V0 was equal to 1 volt. Hence, R Thevenin will be equal to 6 ohm. To determine the open circuit voltage VOC, we apply mesh analysis again. VOC is basically the voltage drop across the 6 ohm resistor, which is this one, because this branch and this branch A and B are floating points. Hence, no current will flow through this resistor. The voltage drop across this resistor is 0. By solving these linear equations, we determined V Thevenin or VOC to be equal to 20 volt. The final step is to draw the